ability of getting good results, right?
That makes sense. That makes sense. Yeah, I think I can do that. And also, did you receive the email that I sent about this summaries about the recent work that was supposed to for the Noah flux? I
Say what it
summarized.
was. What was it said?
It's called a summary for Noah flux. It's an email that I sent to you. Yeah,
Oh,
actually,
somebody for future experiments. I see. Okay.
yeah, actually, Professor Clark asked me to send this to you. Maybe you can, because I write a lot of stuff about like the details of the experimenting and why I did the experiments. And can you take a look at it and maybe cut out something that you think is not important for me? Because it's quite a long document. Yeah, I can definitely do a presentation during the meeting. Yeah, that's not a problem.
Okay, so it's a Word document. I'll have to give you comments on this. Okay.
Yeah, because I lay out a lot of details. Maybe something you might think is necessary to present. Then maybe you can cut it out, and I can shorter my presentation.
Okay.
But I have a
Sounds
good
good.
idea of what I can present. And I'll go ahead and share my presentation for this week for the past 2 weeks. Can you see my screens?
Yep, I can see.
Yep.
Perfect. Yeah, so this is the DI water that we worry about. I think the most part is, I think currently Jeff is opening the line mainly for me because there are two DI water tap at the lab. The one that I use is working and working pretty well, and the other one is completely shutting down. So I was thinking he was just um, giving me a free pass of using the DI water now for my work. And we can see like they are quite cloudy at the beginning when I first got it, and it was slowly fading away and left them with quite a good amount of the air bubbles in there. So the one of the worry I have is when I have like circulating this water with bubbles into the system, the bubbles is pretty visible in the system. But the good thing is the PBS water, the PBS solution I made is with the DI water from the new side of the building, so there are no bubbles, and there are so when I'm doing the experiment, I will always prime the system so there are no any bubbles during any of the experiments. So there are no concerns that raised by this. And when I'm making the next batch of the PBS solution, I'll probably get the water from the DI water tap, and then I will wait it overnight so that the bubbles can go away. Yeah, I think that's pretty reasonable to get rid of the water bubbles pretty easily. So and hopefully this problems get fixed pretty quickly by Jeff and Nick, and repair the leak so that there are no air coming in the water stream. All right. If there are no question about the DI water, I'll go ahead and to the HPLC with the lower center. So this Monday, I have two injection in the HPLC. The one is the 0.5 gram per liter dextran in BSA and PBS that I made 2 weeks ago because Lindsay from the Lorry has been quarantined and was not able to do injection for me for 2 weeks. So I have been keeping these samples at the refrigerator. And so to ensure they are still working, I make a new dextran in PBS and BSA solution that I made on Monday, and then we do put it into injection on Tuesday. So they are freshly made. So I think by comparison, we can see if the PBS, if the BSA solution are gonna denaturize or gone bad or not, like for quite a long period of time. And if the results are the same, and we can continue to calibrate with the old samples, and if they are not the same, then I will make the new samples of the dextran in BSA and PBS solution for the calibrations. And yeah, the results hasn't come back quite yet. Lindsay sent me an email that he had kept the data at her flash drive, and he was not able to retrieve it and send it to me today, and I'll have to wait for her to send me the result on Monday. But the bad news is, in short, she summarized for me that there are only one peak of the death trend and the BSA, meaning there are no separations. For now, I didn't ask. I wasn't able to get any more information from her today in the email, but I will probably go to her office and ask and if there are any better way to get a separations. Because when there are only one peak, we can't do this calibration. We have to see the separation first, then moving on.
So I want to ask you. So last time when you did your results, you were only looking at PBS and Dextran, right?
Right.
You didn't add BSA.
No, yeah. I didn't add the BSA.
And so here, Dextran and BSA seems to have only one peak. So you can identify Dextran pretty easily in your PBS, right?
Yes.
And you can identify BSA and PBS pretty easily, but like the Dextran and BSA are all the ones this is the issue.
Yeah, that's just to separate.
They didn't send you any information.
No, yeah, she just summarized it that in short, there are just only one peak, and we will have to figure out something else or change the elution conditions maybe, because I talked to you about Dr. Antonio and Professor Mosir. They are professors at the Agriculture Biochemical Engineering Center, and especially for Dr. Antonio, he is working on a project similar that is using the HPLC with proteins like albumin. So I think he will have a good idea of what went wrong in this setup, and hopefully I'm pretty confident that this issue can be fixed. But for the current project, like ongoing, from the process, we don't need the HPLC capability right now, though. But we just that we are not in desperate need of this like technology. So I think we can like having this sort out like over time. There shouldn't be a problem.
Yeah, and so I guess Q, do you have any thoughts on what should be done?
Sorry, I have a call from Melissa, so I missed many.
I think I can.
Okay.
Yeah, I can summarize it a little bit. So we did like 2 injection. The one with they are both the same, but ones are made like 2 weeks ago, and ones that is made like on this Monday, and we do the injection on Tuesday. So this one is freshly made. So for these two comparison, we are able to see if the BSA, which is the proteins in the solution, are they going to denature over time, or probably gone bad, or some other reactions happen to them, or if they are the same, if they are stable or not. But the bad news is that from what I heard from Lindsay today, she was not able to show me the entire results because her data was stored at her flash drive, and she can't send it to me, and I have to wait until next Monday. But the bad news is there are only one peak of the Dextran and BSA altogether. So meaning there are no separation between the Dextran 20K and the BSA, and we aren't able to isolate the Dextran concentration from the current process. We will have to analyze more of the results that I get from next Monday.
Yeah. So Q, I guess, what are your thoughts if this whole separation doesn't seem you can't really distinguish between Dextran and BSA? Do you have any thoughts? Maybe what to do, how to move forward?
But I think then the column for HPLC will change the result. So if you have longer column, then could it possible to separate the dextran and BSA?
Yeah, you said you were running originally. There's two different columns you were looking at. I don't remember which one you ended up picking.
Yeah, there are a shorter one and a longer one. So, yeah, actually, there are quite a lot of things to adjust that we can manipulate, like the elution volume. I'm sorry, the elution flow rate, like how fast the elution flow, and there are longer columns that probably we can get the better separations between material from materials, but the resolution on the other hand may be it's gonna suffer from the lower resolution. But yeah, I think the main solution for this problem would be to talk to Dr. Antonio, because he's working on some similar albumin, probably some human proteins in the plasma, and he will have a good idea of what went wrong in our process, and he also using the HPLC in her experiment as well. So yeah, go ahead.
Yeah, I think also one thing that you may think about is, I mean, like I think Andrew Zidney and a bunch of other people have used columns in the past, right?
Yeah.
Separate dextran and BSA. So do you have a good idea what columns were used, what were the column lengths and all that for what was done in the literature?
Yeah, I think that's also my another thought as well, is because currently we only have 2 columns at the lab. This one we can probably adjust some more setting to probably make it work, but I will have to rely on Lindsay and her colleague, Dr. Antonio, to have fixed this problem. I can't really I can ask for like many experts that have done this before, but it's just there are really low chance that we use the same columns as they are. We are just using what the lower center has to offer to us. Yeah. So I think we have to probably stick to what we have, and then on top of that, we can make some adjustment to make it happen. I think that's some ideology moving forward for. Yeah.
Okay, so so you think we have to basically use the column that they provide rather than buy a column that's something that use a column that like Zidney would use.
Yeah, because but
I think even looking at that and giving that information will help them maybe get an idea what is the specifications needed for a column. Separate dextran and BSA.
Yeah.
I don't remember all the details of the column that you're using, but it probably is not long enough, right?
Yeah, that's a good point. Yeah, I'm wondering maybe Dr. Sydney, because she's in collaboration with NovaFlux right now. I wonder they will probably show up in the next meeting with us, probably next week. Maybe I can ask him directly during the meeting if Dr. Andrew is there. And yeah, on the other hand, I'll prepare a list of questions. If he's not here, I'll probably shoot Dr. Andrew an email about these issues and get his thought on this.
Okay.
Yeah, I was expecting there will be separation pretty easily because of the molecular weight differences, but I would have to know what.
Yeah, dextran is like what? It's like 20K roughly.
Yeah, 20K, 15 to 25.
BSA is what?
66. Yeah.
Yeah, it's actually quite a big difference.
Yeah. So I was from I don't know like what conditions like Lindsay was using, but I'm probably gonna go check with her on Monday and get more information on this. Yeah, I'll go ahead and moving on with the clearance experiments that we planned with the PBS. This is the slide from the past presentation. Then I'm going to do the dextran 20K in conventional that I did, and I do the outside in this week, and I'm going to share the result in a minute. And for the sieving coefficient experiments that we discussed about with Professor Clark and you last time, I also did this experiment this week, and I'm gonna show you the results um, in next slide. So here are the clearance experiments result with the outside in. So the clearance is a little bit better than the conventional, from outside in and conventional. And regarding the
Okay. But for myoglobin outside in, so
yeah, for myoglobin, I
Hartog
haven't
showed,
done any
Hartog
outside
showed
in.
that Hartog showed that outside in and conventional had the same clearance, right?
Not
For
quite, yeah.
myoglobin.
I'm probably gonna just lay it out to you here at the from the final report from Fasar on the myoglobin. Outside in clearance is better, but not like by a lot. It's 99.3 and 94.4, not 94.5 of the clearance at the REC 21R. But for the so it's slightly better. It's not the exact same, but it's slightly better. And for the Destran, it seems like it's quite some it's better in like about like a same magnitude, yeah, from 41 to 40.
It's like significantly better, right?
Yeah, quite significantly, I would say, yeah. And yeah, I think that can be like as that agree with what we got for the sieving coefficient that we did by conventional and outside in. Outside in have quite a large advantage over compared to the conventional mode. Yeah, so. And I'm going to tell you all about the procedure and what conditions that I do to get this result. But yeah, this is just overall results with the clearance experiments and the sieving coefficient experiments for Destran in the NIPRO. Mm-hmm.
Outside for
Yeah.
this one is like, let's see. So the C is better, obviously a lot better clearance.
Yeah.
But,
yeah.
Okay, I'm a little surprised by that. I mean, I'm so a little. Oh, but okay. Mm-hmm.
Yeah. And yeah, I think the main reason is because Destran has a much bigger molecular weight than I'm just like discussing like what is in my mind. So for when we are doing with the vitamin B12, because it's so small, the sim coefficient may be pretty large for both modes. So they are pretty close in terms of clearance. And when we have like larger moleculars, like the myoglobin, it's larger than vitamin B12 definitely, but not as big as the Destran at 20K. So I think so that's why the clearance is like getting the differences between the conventional and outside in is getting bigger and bigger as the molecular weight increase. Does that make sense to you, Professor Nottingham?
Yeah, but I mean, I'm trying to think if there's zero ultrafiltration, you're going to have some going through this way, and, and then you're going to have some back filtration, right?
Yeah.
So it depends on what the crossover point is, because, right, if you have the crossover point exactly in the middle, then it doesn't matter whether you go inside out versus outside in, right, for the clearance, because half of it is going to go one way and half of it's going to go the other way, right?
Yeah, but like with the same, like you said, the crossover point. So you meaning the forward filtration and back filtration, the surface area are the same. But what we're talking about is the sieving coefficient, though, which means like when we have the larger molecular weight molecules, we will have a lower sieving coefficients, right? Because it's larger, it's harder to sieving through the membrane.
I understand what sieving coefficient is. I'm saying that, okay, so you have stuff that's moving. Let's just say you have, this is like the stuff inside the fibers, this is outside the fibers, right?
Mm-hmm.
Okay, if you have no net ultrafiltration, that means there's going to be some liquid going up here and some liquid going back, right?
Right.
So it has zero net ultrafiltration. There's a crossover point. in which fluid's going this way for one half, and then the fluid's going this way for the other half, right? So it's a crossover point, and it's presumably near the middle.
Yeah.
Okay. Okay, so if there's a crossover point near the middle, that means the molecules are being sieved this way, right? Are going this way
Right.
in the first half, and they're going this way in the other half.
Yes.
So if you're doing outside in versus inside out, right? It goes this way and then this way, or this way and this way, right? I mean, it's basically, it'll be similar, right?
Yeah. I think it will be, yeah.
So the clearance, I would have expected the clearance to be somewhat similar.
Oh yeah, so yes, the crossover point definitely matter. Yeah. I understand now. Yeah, that was my my bad. Yeah, I would think about that.
So no. So I'm just surprised, right? I mean,
well, to explain this, there might be the crossover point is not in the middle, right? Maybe since when like for example, when we are in outside in, the sieving coefficient is better than the inside out. So meaning the outside sieving, the crossover point is more towards, meaning the surface area for the outside is larger than the surface area from so back filtration is larger than the forward in terms of the surface area, but the flux are the same. I'll give it some more thought.
Maybe I'm mistaken, right? Because if the sieving coefficients are slightly different for one side versus the other, maybe.
Oh yeah.
Because maybe what happens is, although if you're going one direction, if you're going this way, right? The molecules, if you're going from inside to out, right? Like this, you start high concentration here, you're going to get molecules clearing this way, and then when it goes to the other side, it starts clearing back because of back filtration. But you'll probably get a higher flux. Than here. So then if you're doing outside in and it has a better sieving coefficient here, you get a higher flux going this way. You'll get some back filtration in there, but it may not be enough to offset the higher flux at the beginning. So that's probably what's happening.
Yeah, so
Does that make sense, or?
I think that makes sense. Yeah. So for the clearance, we have like forward filtration and backward filtration. But for the sieving coefficient, I'm going to reiterate what we did with the sieving coefficient experiment.
Can I see slide 6?
Slide 6 is just the clearance experiment data that we got the alpha, which is higher than the outside in. So basically, it's the result of the outside in. Because I want to show you the sieving coefficients. This is the slide from the last time that we discussed. And here, I want to show you that we have one inlet from the blood beaker, and this is the outlet at the blood side. And we will have filtrate penetrating through the membrane and get it out with the other outlet. So for the sieving coefficient, we are only getting the sieving coefficient from one side. So only forward, filtration. So I think this number can be saying that at the conventional one, which is from the fiber inside to outside, it has a worse sieving coefficient than from the outside to inside. If that makes sense. And in terms of the, I think that's the reason that we are seeing the outside in is better than the conventional because of the sieving coefficient.
And rather than for myoglobin, the sieving coefficients are probably somewhat similar, right? More similar.
Yeah, I can actually do a sieving coefficient experiment with the myoglobin. Yeah, I can do the experiment though. Actually, we have some preliminary data from the literature. So for the so this actually I want to talk to you about for the sieving coefficient experiment, what testing conditions that I use. So here we have so I want to tell you that there are international standards. The one is the EN1283, which is what Professor Clark talked about, and there's the other one called the ISO A637. Yeah, this paper that I see are analyzing like different dialyzer company, what standard they are using. So yeah, the common standard are using the human plasma and QB and ultrafiltration rate to be 360. And some are doing the human plasma with higher uh, QB and higher QUF, but most of the company are using the 360 combinations. So here are some like bigger dialyzer company like we were Clear, Polarflux, and we have Elisio and some other. So the star meaning this company has not identified what testing conditions they use. But for the two star here, like the Elisio and the HI18, they are using the 360 combination. So that is the testing conditions that I use for the Simon coefficient experiment.
Yeah, and the only thing is you didn't use plasma, but you
Yeah,
used
yeah.
EBS.
So all this data is doing with the plasma, so it's not really related to us. But for the Elisio, for the myoglobin is around 22%. It's much even lower, yeah, with the plasma, with the fouling. So yeah, so that's what we got from the Simon coefficient experiment, and yeah, so yeah, I want to briefly talk about the procedure as well. So
before we start about the procedure, I need to actually step out for a bit. I need to, the person
okay,
to
yeah,
finish.
go ahead.
So I just need to go and just check it out and pay. So we can take like a 5-minute break. Is that okay for both of you?
Yeah.
Yeah.
Yeah, go ahead.
I'll just keep it here, and I'll come back in 5 minutes.
Okay.
Okay, I'm back.
Great. Yeah, so the reason I want to talk about the procedure is because the deceiving coefficient experiment is like the new experiments compared to the clearance. So I want to uh, discuss a little bit with what I do.
I didn't get that. Could you?
Sorry about that. So yeah, for to get the 360 combination, I set the first pump to be 300 and the second pump to be 240 so that they have ultrafiltration differences to be created to be 60. And I will wash the cycle with the DI water. Then I start then I can start the deceiving coefficient experiment. So I'll first priming the system with 1 liter of the solutions, meaning I will drain the outlet, the 2 outlet to the drain, and then after 1 liter of the solution left, I will switch to the full recycle mode, meaning all of the outlet will be recycled back to the beaker.
So say just one more time, just make sure I understand.
Oh yeah. So I will prime 1 liter of the solution so that they will fill the system with the PBS solution and the dextrin solution as well. So after 1 liter, I will switch all these outlet and recycle them to the blood beaker. So what's coming out will all coming back into the blood beaker, and then from there I will record the concentration of the filtrate, concentration of the beaker, and the concentration of the outlet. So here we have the concentration of the filtrate at this side, and the concentration of the outlet at this side, and the concentration in the beaker. And with these 3 values, we will be able to get the deceiving coefficient from this equation.
Okay, and the deceiving coefficient shouldn't depend on the concentration of the inlet concentration as much, right?
Yes, because
if we double the concentration of the inlet, you should still get the same deceiving coefficient, right?
yeah, exactly. So yeah, and then after like I get the data at time like 10, 20, and 30 minutes, I will swap the dialyzer from inside out mode to outside in mode. Yeah, so this way I can get the deceiving coefficient for the both mode. And I will repeat the procedure from step 3 to step 5 within the outside in mode. Yeah, and that's how I get the 2 deceiving coefficient at the same time.
Okay, so it's swap the dial. Okay, that's fine. Yep.
Okay. So yeah, regarding the deceiving coefficient over time, here are the original data with the CL, CT, and C filtrate over time, 10 minutes, 20 minutes, and 30 minutes. And the number highlighted is the average of these 3. So they are all pretty consistent over time. That I measure it and analyze it with the refractometer. And that's the deceiving coefficient value at this particular time, and the average is what I get for the deceiving coefficient for the inside out mode. Yeah, the initial concentration I set as 1 gram per liter because I'm pretty confident and I have a lot of benchmark with this value, and it doesn't quite matter what concentration is using as long as the concentration of the CL, CT, and C filtrate is known. And yeah, here are the number for the outside in mode. They are all pretty consistent over time from 10, 20, and 30 minutes. And the only one thing I want to point out is for the difference between the inside out and outside in, the CT and C filtrate are pretty consistent. So for the outside in, for the C filtrate and CT over time is 0.69 and 0.41. And in the inside out is 0.42 and 0.73. They are like not the exact same, but they are pretty close, except for the C out. Yeah, for the CL, for the inside out mode, the CL, the average is 1.03. But for the outside in mode, the average is only 0.82. So there are about 20% of the differences here. That is mainly causing the differences between the CV coefficient as well, is by the concentration of the outlet.
So outlet is okay. So outlet, so C in and C out. So C out is the what you're measuring, right?
Yeah. The CL is the one that is getting out here, and filtrate will be getting out here, yeah, through the membrane. So CL would be like didn't leave the membrane. Yeah, and that's mainly cause the difference of the CV coefficient is the concentration of the outlet. Yeah, and yeah, we are also so that the outside in mode is better than the conventional in terms of the CV coefficient, and we also get a higher dextran 20K clearance that is better in outside in mode than the conventional ones. And the Fassage data on the myoglobins, since they are all middle-sized molecular, so in terms of the myoglobin, the clearance in outside in is better than the inside out as well. So which agree with what we find. So do you want me to like present like what we have discussed and what we have found in terms of middle-sized molecular clearance and CV coefficient and present it on Nova Flux meeting?
Yeah, we want to send it to us. So is it Monday? When is the meeting?
I don't know. I think you give some time frames, Monday and Tuesday.
I gave a bunch of times, but I guess I haven't heard, so I don't know what date it is.
Yeah.
You should have slides ready for Monday, but
okay.
You should ask to share and share with me and Bill so we can look over it beforehand.
Okay, yeah, definitely. Yeah, because
for me, the question I have for this is, I mean, you only took 3 data points, and it's still like fairly noisy. It's not the most.
Yeah.
Data,
I think that's the problem with the refractometers. So when we have like let me show you the data that I get for the CV coefficient. Right, and can you see my screen on the Excel sheet? So at the top part here that I highlighted, so on the left hand side are the inside out and the right hand side is the outside in. And so the 10 minutes, 20 minutes, and 30 minutes time point, and yeah, for outside in as well, 10 minutes, 20 minutes, and 30 minutes. So we can see, sort of using this C-filtrate as an example, 1.33481. And the other one is 1.33480. So there are only really slightly differences at the 5th decimal points. And for the CT, so the because we are recycling, everything is recycling to the blood beaker. It should be the same the whole times. So when it reach the steady state, it should be the exact same and shouldn't be like fluctuating by a lot. But with the refractometer that we had, there are still like a 0.00001 of the difference. But it's like 1 out of 6.
So that change 0.0001 of the refractometer is enough to change the concentration by so much.
It will change quite so much because of the calibration relationship here. Yeah, so this is the blood beaker. For the outside in, it didn't change, but for the inside out, bless you.
Sorry. So I mean, I'm just thinking for like the C filtrate, so it goes from 0.46 to 0.38 with the 0.0 with the 10 to the minus 5 change in the refractive index.
Yeah, for the filtrate, and that is just one change in the 5th decimal points. So that's pretty huge. Yeah, I can see.
That's really, so I mean, basically you have very little I mean, this data is like, first of all, can you really trust a change of 0.00001 in the refractive index? I mean, that's a very, very small change. What is the what is the level of certainty you have in your refractive index measurements?
I would say if we have more points and taking the average of it, I would have like higher confidence. But for now, like you said, yeah, the one of the fifth decimal points can cause quite a lot of differences in terms of the concentration wise. Yeah, it would cause quite a lot of difference. But yeah, so yeah, so we can discuss like that from the 10 minutes to 20 minutes. These are the difference from 0.52 to 0.43. Yeah, it's quite a lot of differences that it made. And if we're taking more points, I think, and average out, and we will see a higher confidence with the sense.
And what is, so 0.52 to 0.43, and what is the other one?
And
No.
0.45, yeah. So this is the differences, but yeah, but there are 3 values. So I think the best case scenario is taking more points over the time, and we can get a more good idea and try to then can minimize the measurement error that from the refractometer.
No, I mean, when I see this, I'm like, I see, first of all, okay, when you're doing a refractive index measurement, what is the level of, how confident are you? What level of confidence do you have in terms of the measurements?
And that will
because,
be.
I mean, so what is the level of accuracy, right? In this refractometer, is it times 10 to the minus 5?
Yeah. So yeah, I would be 0.00001 from what I can see, but from what the company claims is 4. Yeah, plus or minus. But what
Yeah,
from what I'm experiencing is just about 0.00001. Yeah.
Yeah, so I mean, if that's the case, it's within the, any measurement will be within that. If there's like small changes, you can round up to plus or minus 0.001, right?
Yeah.
So, I mean, in just a small change in that gives you a fairly big change in concentration. You're saying, according to your calibration.
Yeah.
So there's going to be like significant error in your in your receiving coefficient measurement, right?
It's actually not quite a lot in terms of like single value. So when you see the C concentration of the C out is like 0.69 to 0.76, so it's like 0.07 of the differences.
Yeah.
Yeah. So and when we yes, like 0.07 of the difference in concentration. Yeah, and like I said, when we have ballpoints and take the average, it will be better to like help mitigate the error of.
No, yeah, I mean, so I'm just saying there's going to be a significant error in your measurement because any small change in your refractive index can give you a big change in concentration. I mean, at the end, like, I mean, it'll be roughly this, but there's going to be significant error associated with it, the receiving coefficient measurement.
And I have one idea. So maybe, so right now I'm only taking like one test using the refractometer. I can, with the same samples, because I have quite a lot of samples, I can take multiple times with the refractometer. And when it got like a consistent number and it's not fluctuating a lot, I will take that number and instead of just taking one measurement for one sample. Would that help mitigate the problem, in your opinion? So I can like test it multiple times to ensure I can get like a pretty accurate.
Okay, so what is your? Can I see your calibration curve? I mean, also,
Yeah.
You're basically every 10 to the minus 5 change, you're seeing a change in 0.07 in your. I don't know what is this. What is units for the y-axis?
Yeah, actually have it in the. Yeah, the calibration curve is like this. So y equals x minus 1.3475. So y is the concentration, and x is the refractometer values.
And what is Y concentration? What
Yeah,
does it
Y
mean
is
for
the
that?
concentration of the filtrate, the outlet, and in the beaker. Yeah, is the
What
concentration.
are the units?
Gram per liter.
Gram per liter. Okay. Um, and I mean, do you have all the calibration data that I can see to see
Oh yeah,
how?
yeah. Yeah, I think it's here. Yeah, so this is concentration of 1 gram per liter, 2 gram per liter, 3 gram per liter, and 4 gram per liter. So this is the calibration curve equation. And Y value is the refractive index value, and X is the concentration. So yeah, so they will be 0.00013 when there are change of 1 gram per liter of the concentration. Yeah, the way I think that can help mitigate the error by this is to like just for each sample I can take around 3 of the refractometer measuring to ensure that they are mitigating the error from the refractometer itself, and then I can take more samples over time, for example like 10, maybe 5, 10, 15, 20, to have completely 6 data points to help get the um, average of the 6 points instead of 3 points.
Yeah, I think that would be better. At least,
Yeah.
I mean, you see a trend, right? And
Yeah.
so you know it's going to be like around the value you say, but there's going to be right now the way you're doing it. There's significant error, right? And
Yeah.
they're like 0.47 plus or minus. I don't know, like 0.05 or something, right? I don't know. It's going to be like a
Yeah,
pretty big-
0.07.
Yeah, it's going to be pretty. You have pretty significant error in your measurement just because of the way it is. So go down to the next slide, slide 12.
Yeah. So yeah, that's the outside in.
0.544. No, so can I see go up to the previous slide?
Yep.
Yeah, I mean, okay.
Yeah, I think we can like take multiple measurements in the same samples, and then test it with in the refractometer. I can like with the same sample I can like do multiple testing to ensure they are pretty consistent from the refractometer, and then I can use more points to get the average so they can be more accurate.
Okay.
Yeah, because yeah. And the other thing that I have in mind is the pre-filing with the BSA solution. I
Okay.
think we discussed earlier. I think we can also bring this to the table to discuss with the Noah Flux and see. Yeah, I think because this is a brilliant idea that we can like doesn't incorporate a new variance with the BSA, and then we can if the things go well that the BSA is not dissolved into the samples, we can only analysis with the refractometer without using an HPLC as well in this method. So with this pre-filed method. So and the question we bring up last time is, should we let the dialyzer to sit through the night in PBS, or when we file with the BSA solution, we use it immediately, right? And like from what I found, I think the better way is to let the dialyzer to sit through the night in the PBS. And the reason are the BSA solution when there are concentration at 40 gram per liter, the data from Sigma, the solution's stability of the BSA is very good, right? And also with the higher solid concentration, Right now, the solid concentration we have is 60 gram per liter to simulate the concentration of protein at the blood plasma. So that's we have a less water activities and longer the shelf life of the solution. And using the founded membrane immediately, we may have suffered from the BSA's dissolution when we are doing the clearance experiment. So they will probably incorporate a new variance as well. So I was thinking we can let the dialyzer to sit through overnight to let the BSA that is fouling to dissolve overnight, and then we can rinse it and then use it for the experiment as well. And we can analyze pretty easily with just the refractometer, because we know there are very few BSA that is in the sample, and we should be pretty good. But this is the case when we have a pretty high protein concentrations. But the real case is when we have like protein fouling in the membranes, it will be it will actually be quite dilute, right? Because the fouling in the membrane, in the solution there are only, I don't know like how bad the fouling will be, and how like, is it highly concentrated or actually it's pretty dilute. I'm not sure, but I've put in my mind that let this dialysis sit through the night in the PBS will be the best possible case for us for analysis as well.
So are you going to be doing 60 grams per liter?
Yeah, we'll be doing 60 gram per liter to pre-foul the BSA solution, to pre-foul the membrane. But the thing is, after the pre-fouling for 4 hours of circulations, we will rinse it with the BSA. I'm sorry, we will rinse it with the PBS. Basically, we will clean all the BSA out except for the fouling part, right? So yeah, we don't know how like dilute or how easy will the fouling BSA will be denatured or going through some other reaction, but I think letting it to sit through overnight will be the best case scenario, and we can probably discuss with NovaFlux as well. Yeah, so I think the two main thing I'm going to bring to the table with the NovaFlux is the first, the recent process I get with the dextran 20K in terms of clearance and sieving coefficient, and I would think more about the crossing point that you mentioned in the clearance, and also I will discuss about the profile BSA methodology to simulate the effect of fouling. And yeah, and that's what I had for the past 2 weeks. And
Okay. Yeah, so I think you need to just check the clearance measurements and make sure that they make sense. And then you can have a drawing kind of what you expect as happening to explain the results that you see. I mean, what you say makes sense, I guess, but you should have like you should be able to explain that in the presentation, right, that you're giving later next week.
Okay, yeah, I can definitely. So I should probably imagine the meeting to be on next Monday, and then prepare the presentation during the weekend, and I can send it to you to preview it. Okay.
Yep.
Okay. Yeah, not a problem. Yeah, I should have.
All right. So what are the experiments you're planning on doing? I guess, are you planning on doing more clearance experiments, or are you planning on doing this pre-filled BSA? I'm just trying to understand the next week. What are your plans?
Yeah, I think I would probably redo the sieving coefficient to do it like with more, trying to mitigate the error by the refractometer and the experiment itself. Yeah, I'm trying to get trying to mitigate this and redo the sieving coefficient experiment. Yeah, that's the main point. Regarding the clearance though, I think this 2 number is pretty like telling the story. And I would just probably mainly focusing on getting this value to be confident enough to. Yeah.
Okay.
And when I'm confident in the sieving coefficient, I'll probably move on to the pre-fouling area, but I will have to like discuss with the NovaFlux first. If that makes sense to you. Professor Nottingham?
So Q, is there anything you want to discuss?
I just mentioned three things. The first thing is we only have the clearance for myoglobin comparison between inside out and outside in.
Yeah.
So it would be great if we do the clearance test for the myoglobin, so we have the same tendency.
Yeah, if we get the same thing, then at least you know what you're doing. It sounds reasonable. Otherwise, there's something weird going on, right?
Yeah, I can. Yeah, because we have some previous data on the myoglobin. I can do the outside in as well to compare with this. Yeah, no problem. Yeah, good point.
Yeah. And the second thing is, as Vivian mentioned, we need to get more measurement for sieving coefficient.
Yeah.
Make sure whether it is just error or it is showing the same tendency.
Right.
And the last thing is, if we prefer the membrane with DSA, that means, so if we cannot recover from the fouling, then it means we consume the dialyzer, but we only have two Nipro. Is that correct?
Yeah. We only have two Nipros, so
yeah. So that is one thing we need to think about.
So you mean when we pre-filed the one with the Nipro, I think it can use for multiple experiments afterward with the PBS, so it should be no problems.
But if we want to get some data without fouling, then
we can't go back with the we can't go back. Yeah, that's a good point. Yeah, I will have to like do all the experiments.
How many Nipros do you have left?
Two.
Two.
Okay.
So one is currently using.
Yeah, one is currently using. Yeah, once we filed it, we can't go back to the unfiled stage. Yeah, that's a good point. Yeah, Q. Yeah, thank you for the opinions. Yeah, that helps a lot.
Any other comments, Q?
No, that is everything that I have.
Are you okay, Professor Nottingham? You seem quite tired.
I am just falling asleep. I don't know. Maybe I just didn't sleep so well last night.
Yeah,
days.
Yeah,
I'm sorry. I apologize.
It's fine. I worry you might pass out for a few seconds. Yeah, I'm just make sure you're okay. Okay.
I'm just one of those days. I'm sorry.
Oh, you're fine. You're fine. You're fine. Yeah. Yeah, and that's all I have for today. And I'll prepare the meeting. Prepare for the meeting.
Yeah, so just make sure you send the slides to us. Do you have it recorded, I guess?
Yeah.
Okay, so
I'll send it to Professor Clark as well.
Yeah, but I think what Q says is fine. I think make sure you get the sieving coefficient. You're careful. You're fine with that. You make sure you do the clearance for myoglobin, right? Outside in, and make sure it kind of agrees with what Farzad has done in the past. Because if that's the case, then at least you can, if you were able to replicate everything that Farzad did, and then you have these results, and at least we can be confident with these results that you just presented, right?
And also, should I? So this is not confident enough, but should I present it to the NovaFlux to give them a preliminary idea of what I'm doing to them?
I mean, how much more data can you gather? How long does it take to gather data?
I mean, it will take some time, probably a day for the sieving coefficient experiment to do. But like you said, I have to prepare the PowerPoint for the Monday, right? There's not much time for me to do another experiment. I will have to gather what I have right now and come up with a PowerPoint.
Yeah, I mean, maybe, I don't know. Why don't why don't you just include it for now, and we can decide if you should take it out.
Okay. Yeah. Absolutely.
You can just say that these are all preliminary results. We're getting much better receiving coefficient data
Okay.
as time goes on.
Yeah.
One thing you can do to get, so what are you starting out your experiments with? Are you starting it out with 1 gram per liter?
Yeah. 1 gram per liter. Yeah.
If you start out with 4 grams per liter, it'll be like won't you get much better results?
Not really. That would be get better in clearance, but in terms of receiving coefficient, it's just relatively the concentration for.
No, because you're gonna get much better refractive index measurements, right? You're not gonna see like a change in 10 to the minus 5 will not be like a 7% change in your concentration. It'll be a 2% change in your concentration, right?
Oh yeah, that's a good point. But
and so then you would get like, you're still gonna get something similar to what you're getting now, but like at least there'll be less error.
Yeah.
There'll be less error in your measurement, right? That's another thing you could do.
Right.
I don't. Yeah.
Good point. Yeah.
If you do higher initial concentration, you do many refractive index measurements, and you do multiple time points. If you plot all the data, it'll look like there's a bunch of things that are scattered around the lines, and you can make a nice average, and you'll be like fairly confident in it, right?
Oh yeah. True.
So I think that may be the best way to do your receiving coefficient measurements.
Okay, yeah, that's a good idea. I'll definitely try that one out to see.
Yeah, I just and then.
And do you expect me to lay out the procedure as well? Because this is quite new and haven't done before by Fasar. Should I present it to NovaFlux?
You should bring out the procedure. Just say what the procedure is, so then people also can comment on whether you're doing the procedure okay.
Okay.
It's good to have, before you present anything, it's good to kind of just explain how you did it.
Yeah.
Yeah.
Not a problem, yeah. And yeah, are there any concern or for my future experiments? And yeah, I will conclude what Q talk about the future experiment, and I will conclude it in the meeting next with NovaFlux as well. Yeah, I'll definitely bring that up. Okay.
Yeah, so you can talk. All the things you can say is that the things that we have done is we've basically gotten a refractometer. And before we were doing UV vis measurements, we did stuff with the Rec C21, and we did mostly vitamin B12 and myoglobin. The idea here is we need to move to dextrans. Dextrans, you can't really use UV vis, so we need to basically use a refractometer. So you spent some time, we got a refractometer in the lab, we've done some calibrations, we've gotten some results. We've also, we're thinking of if we want to do stuff with BSA, we need to then, not only do refractometer, you have to have some type of
HPLC capability.
HPLC with a refractometer. So we've kind of contacted people, we figured out how that works. It took a long while. We found resources on campus that are able to do it. We're getting preliminary results for HPLC, and we're seeing if we can get results. And we're able to get results for just pure dextran.
Yeah.
But now we're looking at dextran plus BSA to see what it looks like. In the meantime, we've done some clearance measurements just in the NEPRO, just to make sure, and just what we've observed. And we actually, and then you can state what you've seen so far.
And should I also mention about like the DI water issue?
We can just say that there were some delays in getting some experiments because there was actually some DI water issues on campus in our building. So for 2 weeks we couldn't really get a lot of data. We could run a few experiments, but we really couldn't run at the level. You can say that we can say that, but you don't need to put that in slide form.
Okay, I see.
Yeah,
I got you. Yeah, not a problem. Yeah, I think I can handle that. Yeah.
Everything else okay?
Pretty good. Yeah, it's good to like have the DI water bag than just sitting around and handling
Yeah,
anything.
and how is your wife doing? Is she okay?
Oh, she's doing pretty good. Yeah, she had some bleeding, but it turns out that had nothing to do with the baby, so it was good.
Okay.
And we
Yeah,
just
it's always scary when you have bleeding
yeah
with the baby. So there's always so it's good that everything's okay.
yeah
Make sure
yeah
she's make sure she gets lots of rest and
yeah
is fine.
yeah
That's good.
yeah. Thanks for asking though. Yeah
And then everything else is okay otherwise?
yeah, everything's doing smoothly. Yeah, and I think I can get more experiment done and pretty easily right now. And I'll probably there's one more thing. So when if we're doing the prefiling, we have to order more BSA for that, and then probably some more PBS materials like the sodium chloride or something like that. We will have to Then that's the for because I want to like speed up the process of the experiments because we have some delay. Yeah, I can do more experiments with the time that I left. Yeah.
Okay. I think that should be fine. Q, is there anything else you wanted to add?
No, that I think everything has been mentioned.
Okay. If that's the case, I think we can call it good. Thanks, CG. Just make sure you get the slides ready, and if Q,
Yeah.
if you need help, you can help.
Yeah,
CG with
let me
slides.
know if you need something from MIL.
Yeah, from now I think I'm fine with that because I have like presentation from each week, so I can just gather information from each of them and gather them together. Should be fine. Thank you for the offer, Q. All right, yeah.
Okay.
Get some rest,
All right.
Professor Nottingham.
Yeah. Thanks. All right. I'll catch everyone else later. And
Yeah.
Q, I guess I'll just talk to you on phone after this.
All right.
Okay.
Everybody have a good weekend.
Okay.
Yes.
Okay.
Bye.
Yeah, bye. Thanks.
Bye.